Okay, Assalamualaikum and good morning, everyone. So we continue with our lectures. We have only a few lectures left. So let me just say the following. We need to finish off a certain amount of topics. So if we didn't get to finish it by this week, then I will upload all the necessary materials, lecture notes as well as recorded lectures, so that you can actually go over it, and if you have any problems you can always consult me. Okay, so we'll try our best to see how far we can go through this week. I've also uploaded your SCL module, for which you need to do it as a group of 4. Okay, so you can use your assignment group, and then combine 2 assignment groups to get 4 to get a group of 4. Okay, so please have a look at that, and then it's already uploaded on Putra Blast. So each group will have to identify which paper they are going to review, and then probably you can discuss it in the WhatsApp group. So most probably the deadline for this will probably during the study week. Okay, so I hope that's okay with you. Right, so let's move to our lectures. So last week, let me just see if I can write this. Last week we had gone into Maxwell Boltzmann distribution of velocities. So this is a particular technique, just trying to transform what we had was actually looking at it in the form of energy states written in terms of wave numbers. Okay, going from wave numbers to the speed. Okay, these are wave numbers, and then u with speed. So that is just a sort of simple exercise of transform a particular distribution to another distribution. Okay, so for today, let me get rid of that red pen. For today, we are going to continue with doing some calculation with this kind of distribution. So, and one of the things that I think I mentioned at the end of the last lecture was to calculate given, say, a distribution f of k, then one can calculate average values of any quantities. Okay. Of quantities, say a, by doing the following integral. So this is the average denoted by this bar on top. So you just simply integrate that distribution together with the function that describes the quantity as a function of k. Okay. So you need to integrate that. That goes from 0 to infinity, and then simply divide this by the distribution of fk 0 to infinity. So you can see the analogy with the case of the bottom one is like your partition function in a way. Okay, so okay, I've forgotten to bring my mouse today, so I'm going to use the trackpad instead, which is a bit harder to push. So bear with me, I'm going to be slower in this. Oops. Let me see if I can just use a pointer. Okay, never mind. So, okay. So, how can we prove this is to use the Boltzmann distribution. Let me just write that down. So okay, so proof. So from statistics, you know that your average value is simply equals to your probabilities multiplied by the quantity, okay, and then sum over all possible k. So in this way, it's just the same thing. You use Boltzmann distribution. The fact that now this is again why we have gone into this integral thing is because in classical mechanics your quantities are actually continuous, unlike the case of the quantum cases where your energies, for example, are given in terms of discrete quantities. So that's one of the difficulty with this thing. So yeah. Okay, let me push this thing up. So so how do you do this? What we do is now to replace that by an integral. Okay, so again we have your AK first, so that's the most easiest to think about. And then what about the probability? Well, the probability will be given by the Boltzmann distribution thing. Okay, with T divided by the partition function. Okay, whatever that is, we have not calculated it. And then remember, you need to integrate with respect to k. So there must be a density of states. Okay, so this gives you the density of states, so that when you integrate, you are taking into account of all possible states described in that particular, say, 3 dimension, for example. Okay, so this is density of states. Sorry about this. Come on. I've forgotten to bring my mouse today, which should simplify things, but give me a minute. The trackpad is a bit difficult for me to use, so that's the reason why. Oh dear. Perhaps the easiest way to clear off this thing, then I can just restart everything. Let me clear that off. Okay, so I can just simply write over. So let me just rewrite things again. So you have A bar given in terms of integral 0 dk ak, then your probability here kbt and z. Now we do not know this yet, okay? So what do we do? The only way we can actually get to sort of dispose of this quantity is to just remember that this is supposed to be a kind of normalization. So now instead consider the case where a equals to 1. Okay, so then you'll be getting the following. So the average value of 1 is always 1. So but then you have an expression over here, the k times 1 here, and then exponential epsilon k kbt over z times the k. Okay, so remember that this is essentially a particular value. Your z is particular value, so you can divide this by, so divide a bar by 1. Okay, so I'm going to need some space again. Hopefully this works. Okay, good. So a bar then will be equals to the integral of dk of ak e minus epsilon k kbt dk, and then you it's supposed to be divided by z, but I'm going to divide by the one above, which is also having a z. And essentially the z on the numerator and the z in the denominator will just simply cancel out. Okay, so this then you can now replace back the idea of this is supposed to be, let me put this in red. Okay. This is supposed to be your f of k. Okay, so replacing now with that, so this will be equivalent to saying, okay, I have this, which is the thing that we wanted to prove. Okay, all right. Let's try to work out some examples. Let me just see what do I have here. Okay, so probably I need a lot of space here, so I'm going to just clear this, and then what I'm going to do is to work out the calculation for average value of wave number. Now if you remember, if you use the quantum physics kind of relation, your wave number is going to be related to the momentum. But okay, let us just calculate this. So k bar will be simply equals to integral of f of k times k dk divided by integral of f of k dk, and the distribution that you're going to use is going to be the following, which is your Maxwell-Boltzmann distribution. Which I'm going to write down here so that we don't need to refer to the next calculation. What's going on? Perhaps I need to move this a little bit. Okay, so you just simply plug those in, okay, and then that should give you the following integral. Epsilon k, remember, is just given by your kinetic energy, so that's h bar squared k squared on 2m, and then multiplied by kb t dk. Same thing there at the bottom. Okay, so our problem is now to actually do the integration. Why we are doing this, in fact later on we'll again have to look at this kind of integrals when you discuss the Planck distribution. Okay, so when we talk about black body radiation, we're going to go through this kind of calculations again. So let's try to do this properly. So again, I'm going to avoid moving my board. I'm just going to clear it. Okay. So what do we do in this particular case? Remember, it's the integral of k cubed, for example, multiplied by the exponential square. So I'm going to just replace it by a simpler what you call variable, and then your dk will now be given by 2m kbt h bar times dx. Okay, so now I'm going to replace all the k in terms of this particular x. So k bar will now look like the following, which is now simpler for us to look at, but still you need some knowledge of integral over Gaussian functions, which we will do in a minute. Integral x cubed e minus x squared dx 0 to infinity divided by integral of x squared exponential minus x squared. Now, what are the identities that you need? Is the following entities of Gaussian integrals. I will call this as I to n for the case of even numbers, is to integrate this x to n with the Gaussian function. And the answer should be, one could actually do this proof much more systematically, but I'm just going to just write down the formula. So what happens over here is that you can sort of do a repetition, so iteration of integrals, and then you get all these factors coming in. So if this is 2n, then you have 2n minus 1 is going to be an odd number, so that odd number will multiply with the smaller odd number and until it gets to 1, and then the whole thing multiplies by square root pi over 2, which is the case of when you the answer when you get well, the answer that you get for n equals to 1 would be square root pi over 4. Okay, so there is a shorthand notation for this, since these are like multiplication of odd numbers on the numerators, okay, on the top, okay, and it multiplies from the specified odd number to the smallest. In this case it's equals to 1. This is sometimes denoted as this is sometimes denoted as 2n minus 1 double factorial. What does it mean is simply to skip the even numbers, okay, and just multiply the odd numbers. So 2n minus 1 double factorial over 2 n plus 1 square root pi. Okay, so that is for the odd case, even case. For the odd case, it will be even simpler. Again, one could prove this in a more systematic way, but I'm just going to write down the answer. So integral of the odd case is given by x 2n plus 1. Okay, so unlike this is even, this is now odd. So integrate with the Gaussian function, and that gives you just n factorial divided by 2. So we're going to use this formula to evaluate here. Okay, so let's just do that. So you can actually see over here, the top one I will be using the bottom formula, and then for the bottom case I will have to use this formula. Okay, so let's see what the answer is. So I'm just going to clear this so that I can avoid moving the board. So the answer here is given by k bar equals to, you put the right formula in, then you should be getting this factor out. Oops. Control Z, h bar squared and then the top one is just half divided by square root pi over 4. So the whole thing is just square root of 8 mkbt divided by h bar squared. So, and remember, as I said, this is really related to the momentum. So if one wants to get the speed, for example, then you just use the h bar k being the momentum divided by the mass, then you essentially get what you want. Right. So the other thing that probably of interest to us is going to be the average of k bar squared. Okay. So again, this will reduce to this quantity. I'm not going to write everything down. You can look it up in the book. So I'm just going to write the answer here. mkbt on h bar squared. So the integral after changing the variables is going to be x to the 4th on top and x to the x squared at the bottom, just like before. So again, this will give you 2m kbt divided by h bar squared here, and then you need to use the formula again. So the top one is given by this, excuse me, and the bottom one is just square root pi over 4. Okay, and that is really giving you 3m kbt over h bar squared. Okay, and this essentially gives you, if your k bar gives you the speed, this gives you the average value of square of speed. Okay, so that gives you u bar squared. Sorry, I should put the square under the bar here, and that gives you h bar over m square k bar squared, which is 3 kbt over m, which is kind of familiar what we have seen before when you do the ideal gas kind of calculations. So okay, maybe I should mention this. So this would actually gives you the average kinetic energy. So you multiply this by m, say, multiply by m, then you get your average kinetic energy. Which is going to be just 3 kbt. Okay. Hang on. I missed. Yeah. Okay. Sorry. Half m. So this would be equals to 3 over 2 kbt. Sorry about all this problems with the whiteboard. Okay, the other thing one should introduce this stage is to remember when you do kinetic theory of gases, you also given the idea of a root mean square. I'm pretty sure you have seen this before. RMS as speed, okay, which is really taken from your your speed square average, and then you take the square, okay, and then this would actually gives you 3 kbt m square root. Okay, and one could actually try to calculate this. These are essentially possible to measure, and of course the calculation can be coming from here, and you'll find that in terms of say certain example is given in the book is the nitrogen molecules. You have your u bar squared is given by this quantity, Whereas if you do the calculation for the average speed, u bar is going to be 454 meters per second, and you see that the root mean square is giving you a higher value simply because for your speeds average, there are cancellation among the random speeds, okay, but over here everything is going to be positive, and then you'll get your larger values. Okay, there are other sections in the book which I'm going to skip, which is on molecular beam, sorry. So this is just for separate. Okay, so let's move to the things which is a bit more of interest to us, which is Planck's distribution. So again, I'm going to just simply clear it. Okay, so Planck, so this is a different chapter here. So Planck in the 1900s gave the theory of black body radiation. Okay. So, and it uses Planck. What Planck did was actually to use a lot of statistical mechanics ideas, which he borrowed from Boltzmann. Okay, so let us try to do some of the calculations and then explain the concepts before that. So what is a black body? A black body is an idealized body that absorbs all radiations. All incident radiations. Now, when I say idealized body, it's really like a more theoretical concept, because it's most bodies are absorbing radiation. To make it absorb all possible radiation is probably harder, and these are they can be modeled, but most of the time it's going to be very difficult to realize. So let me just say this first. So all objects absorb radiation and reflect some. So that's why you'll be able to see some colors. If ordinary objects absorb all radiation, then it will appear as black. So that's why we have this terminology of black body radiation. Okay, so in a way, in some sense, this is already sort of approaching the black body concept. Okay, but if you want to be more strict, then you have to have some kind of a toy model for this black body concept. Okay, so a kind of a toy model is essentially a cavity with a small hole. So what happens is that, okay, here's a cavity. I'm going to attempt to draw this. So a cavity here looks like a sphere. Doesn't look very good. Let me try that again. Or maybe I try to push this thing out and see if it works. So I can draw it here now. So it's a cavity here, then you have a small hole, and what happens is there's an incident radiation here that goes through the hole, and then it starts to reflect. Okay. And then it keeps reflecting until at some point all the radiation gets absorbed. Okay, so but then there's when the I should mention also that all objects also, maybe over here, all objects also emit radiation. Okay, so in other words, the theory says if you have a good absorber of radiation, then it's also a good emitter of radiation. Okay, the rate of absorption is going to be equal to the rate of emission. Okay, so over here, your black body also radiates. So you have radiation coming out. So this is emitted radiation. And the thing to be studied is to study this emission of this radiation. Okay. So okay, let me just clear this thing up. Okay. So what happens is that when the cavity gets heated up due to the I should mention just now that the cavity is a model for your black body, okay, because it tries to absorb all possible radiation. So your cavity will be heated up to some temperature T, and then the emitted radiation will only depend on this temperature T, as well as the area of the walls of the body, or in this case cavity. Okay, so Stefan in 1879 proposed this formula, dq dt equals to, so it has to depend on the area of the cavity, so there will be an area here, and then it has to depend on temperature, so there will be a temperature dependence over here, and the temperature dependence is actually is T to the power 4, and then there will be a constant over here, which is a Stefan constant. And Stefan constant is around 5.67 times 10 to the power minus 8 watt per meter squared, and then to get the dimension right, he has to take care of that dimension of temperature, so that gives you K to the minus 4. Okay. Now initially this is probably what we call a phenomenological law. What Boltzmann did was to give a thermodynamic basis. Boltzmann 1884 gives a thermodynamic basis. So because of that, it's sometimes called the Stefan-Boltzmann law. Okay, so can we actually try to deduce this formula? Well, we can attempt. So let me just write a few more things. So we say that the radiation density, radiation from the cavity, Control Z, from cavity per second. So per second, that means it's the power really. Okay, just like mentioned before, and it is proportional to the energy density, which is denoted as U. Okay, which is of course it means energy per unit volume. Okay, so one needs to decompose this energy density because one has this possible different radiations coming in of different wavelengths, so you need to be able to actually tell how the energy density depends on the wavelength of the radiations. So into a function of wavelength, and this is sometimes called the spectral density. Okay, because you're going to write your energy density as a function of lambda, and then over an interval, this is given as the radiation per unit volume in the range of lambda goes to lambda plus d lambda. So okay, so we need this concept of energy density which varies with lambda. The other thing that we also need is the fact that your radiation travels at the speed of light. Speed, forgive my handwriting. So this is going to be on C. So in other words, what we're going to have is by this understanding of the spectral density, that means your energy density depends on lambda, you will attempt to rewrite your your energy, what was it called before? The energy that was introduced by Stefan earlier, dq lambda dt should be equals to the area, okay, of the body, and then your speed of light here, and then the decomposition of u lambda d lambda. And then let's consider the case of spherical volume. Then you integrate over the angular elements, phi 0 to 2 pi, and then there's this factor sine theta, which is from the Jacobian, but you also need your cos theta from projection, which is which? Okay, one of them. Okay, one of them is the Jacobian, the other is the projection. And this is integral theta, and that's this 4 pi that was written there. Okay, I think this will cancel off later on. When you integrate this, you get your 4 pi back. So, okay, let's integrate this. So let me clear up. So if you integrate over lambda, so essentially now you dispose your dependence on lambda, so you get your U, your energy density here. So this is sometimes called the total energy density. And then you do the integration over the angles. Then you're supposed to get the following. And this should be equals to the if you check properly the dimension of this, so this is area, this is speed, and this is energy density, so you should be getting power from there. Okay, so now if you divide it by the area, for example, so that means you do QT divide by area here, what do you get? You get CU over 4, which is now identified with your Stefan's law, sigma T to the 4. Okay. So in other words, your U is going to be 4 sigma T to the 4 over C. Okay. So in other words, we have your total energy density being calculated out using the model of the cavity together with the Stefan's law that we had earlier. Okay. So the next thing is to look at another let me just try to finish this because we want to get to Planck's law. Another one is given by Viens. Viens in 1893. Okay, where he used again the idea of spectral density but using some model that he used, U lambda D lambda is given by some function lambda T D lambda divided by lambda to the 5th. Okay, so this is called Viens Scaling Law. And if you divide this by, remember that you had your U earlier, never mind. So the idea here is essentially you divide by this temperature dependence, which is t to the fifth. Somehow this is related to the one we had before, but I've not actually worked it out as yet at the moment. So lambda fifth to the t to the fifth, and when you plot this, okay, plot this as function of lambda t, then all your plots, okay, will be independent of your lambda, and you will produce a particular single curve. So this is an important result that sort of limits the way how things scales with respect to lambda. Okay. So let's try to use this to calculate your energy density again, the total energy density. So what you need to do is to integrate it. And this gives you the following: F lambda t d lambda over lambda to the fifth. And after this, one really has to look at what this F lambda is supposed to be, and this is sort of determined through experiments. Let me try to push this up. Hopefully it doesn't give me problems. Okay, good. So F lambda determined phenomenologically, meaning it's come from experiments, and what one finds is this it should have a maximum. So when it's at maximum, that means if you take your derivative with respect to lambda, which is now given by t. So if you take this with respect to lambda, you have one, you have the lambda dependence in your f. Can you see my cursor, by the way? Somebody? So there are two dependence on lambda here. Let me just, yeah, there are two dependence on lambda here. So lambda over here, and then there's the lambda to the fifth over here. So if you take the derivative, then you get this two terms: the derivative of f lambda t over lambda to the fifth minus phi, which is coming from the lambda to the fifth there, f lambda t over lambda 6. And if it's a maximum, then it should be giving you a 0. Okay. So in other words, what we have is the following. I'm having problem again. Okay. So one has lambda maximum t equals to phi f lambda t divided by f dash lambda t, which could actually be giving you some kind of curve, but no, let's not do that here. But from experiment, one finds lambda max t equals to 0.002899 meter times Kelvin. Okay, so this is sometimes called Viens displacement law. Why is this called displacement? If you look at what happens over here, if you make, say, okay, let me go to a different color. If you increase t, then you'll find that in order for you to satisfy this equation, then your lambda max has to go down. Okay, so that would actually give you some curves. Okay, and if Viens law is correct, just push this up a little bit more and finish in a minute. If Viens law is correct, then all plots should fall into a single curve. So let me just go to the book, because I do not have the mouse for me to cut and paste here. It's going to be difficult. So let me go to the book now and show you the picture. Okay, here's a picture of maybe I should open this through give me a minute, just a little bit more. Open with I think I don't have time. Okay, let me just go to this picture. So here you can see two different black body, two different bodies. One is from a black body, and you can see the area under the curve is much larger over here compared to this body, which is just a tungsten, okay, which is not a perfect black body, and it actually has a smaller area under the curve. So that tells us, okay, the black body is the best sort of emission or absorber of the physical bodies. Okay, so that's one. I want to show that. The other one is this. So this is the case where your temperature is changing. You can see this. Hello? Give me just one more minute, okay? Just want to finish this. So you can see the temperature here, the peaks where the temperature is going to the left, okay, and that shows that it's going to go to a shorter wavelength. And this is the thing, all these plots using different experimental data now been plotted with the scaling law, and it falls into one single curve. So that's the main thing. Okay, so we will talk about Viens proposal again, and then we shall compare to this Planck's law. Okay, so I'll stop there for today. So let me go to you and take the attendance. Sorry about going a little bit more. Why is it not working? No participant found. Let me do that again. Something is not right here. Okay, in this way I would have to save this. I want to save this. Let me try again just to see. Okay, what I'll do is probably can you give me the attendance in the WhatsApp rather than trying to do it over here. Sorry for this. Okay, thank you everyone.
Thank you. Thank you, Doctor. Thank you, Doctor.